avutadi. కనిపిస్తుందిగా ఇది అమ్మ ఇక్కడ ఇన్వర్టెడ్ ఉంది కదా, సో ఇట్స్ ఓకే నా మైండ్. సో ఏం చెప్పడం అర్థం కావట్లేదు, ఎందుకంటే ఎవరు లేడు కాబట్టి. లింక్ షేర్ చేద్దాం కానీ ఫస్ట్ ఎవరికొకరు షేర్ చేసి. కాసేపు బాటిల్ కూడా లేవా నీ అమ్మ? ఒక బచ్చాకు పడదాం. డౌట్స్లో పడదాం. సో ఓకే, ఫస్ట్ ఏం చేద్దాం అంటే ఈరోజు ఐఎమ్ థింకింగ్ కూర్చుని మొత్తం ఎక్స్ప్లెయిన్ చేస్తూ ఉంటాను. ఎక్స్ప్లెయిన్ ఫాలో అవ్వకండి, అండ్ ఫాలో అవ్వచ్చు, బట్ నేను చెప్పేది కరెక్ట్ అని చెప్పి నాకు అనిపిస్తుంది, కానీ ఎలా ఉంటుందో నాకు తెలియదు. సో యువర్ విష్. అదే టైటిల్కి అదే పెట్టాను, గుడిసిపోద్దా, నాకు కూడా తెలియదు, చూద్దాము. సో లెట్స్ గెట్ స్టార్టెడ్. నేను అనుకున్నా అంటే యూనిట్ 1 నుంచి అలా ఒక్కొక్కటి నాకు తెలిసింది ఎక్స్ప్లెయిన్ చేసుకుంటా, ఇది కుదిరితే కొన్ని డౌట్స్, కొన్ని క్వశ్చన్స్ చేసుకుంటా. క్వశ్చన్స్కి ఐ హ్యావ్ రామామృతం ఒకటి ఉంది, బీసీ పున్మే ఉంది, బన్సల్ ఉంది. ఇవి రిఫర్ అవ్వకుండా ఈ థాట్ ఐ విల్ డూ. విల్ సీ హౌ ఇట్ గోస్. సో చూద్దాం. ఐ థింక్ ఐ విల్ కమ్ ఇన్ లైక్ 5 minutes. సో పిన్ని వాళ్ళు వచ్చారు, జస్ట్ హాయ్ చెప్పేసి వస్తాను ఫార్మాలిటీకి. సో యా, we will get started. హలో, వచ్చారు. నేను చదువు చెప్తా, వింటావా? చదువు చెప్తా, వింటావా?
అదేం చేద్దాం, మీకు ఎక్కించావు.
లైవ్ స్ట్రీమ్ చేస్తాను, చదువు చెప్తా.
లైవ్ స్ట్రీమ్ అంటే ఇప్పుడు ఏంటి? యూట్యూబ్ ఎక్కిస్తున్నావా? ఛానల్ పెడుతున్నావా?
ఛానల్ పెట్టట్లేదు, నా దాంట్లో స్టోరేజ్ లేదు. నేను రికార్డ్ చేసి పెడదాం అనుకున్నాను. సో యూట్యూబ్లో ఫ్రీ స్టోరేజ్ వచ్చి దాంట్లో అవుట్. బాయ్
బాయ్ బాయ్.
ఓకే, లెట్స్ గెట్ స్టార్టెడ్. సో ఫస్ట్ R22 ఓపెన్ చేద్దాం పద. R20 నుంచి ఒక్కొక్కటి చేసుకుంటూ వద్దాం. చలిగా ఉంది, ఫైన్ వస్తాం మనకి. R22 ఈ అమ్మాయి అయిపోయి పెట్టుకున్నాడు, ఇక్కడ పెట్టుకున్నాం. R22 ఫోన్ చేస్తే అయిపోతుంది కదా. ఓ షిట్, తప్పు లింక్ పెట్టాను గాయ్స్. నీ ఎది పుగ్గాండి కదా. ఎలా పెట్టాలి? షేర్ స్ట్రీమ్ ఏది? హౌ డు ఐ సెట్టింగ్స్? నో, క్లోజ్. స్టే ఆన్ పేజ్ ఓన్లీ. ఆగు, రావట్ వెతుకుతున్నా. ఓకే, ఇక్కడ ఉంది. కమ్యూట్లో పెట్టుకుందాం. బాగా వస్తుందిలే, పద. నాని లైక్ కొట్టుకుంటా ఫస్ట్. మైదా సాంజికా, మైది బుగ్గలు, ఇంకేది బుగ్గలు. ఓకే, ఇక్కడ చూద్దాం. యాక్చువల్లీ దిస్ బెటర్, ఇది బాగుంది ఇంకా నాకు కొంచెం. నేను చేసే అతికి ఏం వస్తుందో తెలియదు కానీ ఏదో ట్రై చేస్తున్నాను. ఓకే, ఫస్ట్ స్ట్రెంత్ ఆఫ్ మెటీరియల్స్ R22 ఓపెన్ చేద్దాం. ఇంత కొంచెం అంటున్నాను, ఏది పుగ్గాను ఓపెన్ చేయట్లేదు. పేజ్ నెంబర్ 40. ఓకే, మనకు ఫస్ట్ యూనిట్ అన్నట్టు సింపుల్ స్ట్రెస్ స్ట్రెయిన్స్ ఇవన్నీ తెలిసినవే. ఒకసారి అలా లుక్ వేద్దాము కొంచెం. ఎందుకు లుక్ వేద్దాం అందుకే కానీ పద. ఓకే, సో యా. ఓకే, ఫస్ట్ ఆఫ్ ఆల్ స్ట్రెంత్ ఆఫ్ మెటీరియల్స్ ఇన్ స్టార్టింగ్ చూస్తే వాట్ ఈస్ అండర్స్టాండింగ్ ఆఫ్ స్ట్రెంత్ ఆఫ్ మెటీరియల్స్. ఐ డోంట్ నో వై ఐమ్ ఆస్కింగ్ క్వశ్చన్స్ అండ్ ఎందుకు ఎవరు లేడు కాబట్టి అలవాటు, బట్ స్టిల్. సో లైక్ మనము మెకానిక్స్ అన్ని చేసేటప్పుడు లైక్ వీ డీల్ విత్ ఆబ్జెక్ట్స్ విచ్ హ్యాడ్ లైక్ నో డిఫార్మేషన్స్. కానీ నీకు రియల్ లైఫ్లో చూసుకుంటే మీకు ఆబ్జెక్ట్స్ అలా ఏమి అలా ఉండవు. దే విల్ హ్యావ్ డిఫార్మేషన్స్ అనమాట. లైక్ ఇప్పుడు ఇదే ఉంది, ఈ వాల్ ఇదేంటి, ఇది కబోర్డ్ కదా, అది దిస్ కబోర్డ్ ఉంది. యూఎస్కి నాకు ఇది బ్లాక్ బోర్డ్, వైట్ బోర్డ్. సో ఇప్పుడు ఈ కబోర్డ్ నేను ప్రెస్ చేస్తున్నప్పుడు నీకు అక్కడ డిఫార్మేషన్ ఏం కనిపించట్లేదు. బట్ ఇన్ రియాలిటీ అక్కడ చాలా డిఫార్మేషన్స్, లైక్ మైనర్ డిఫార్మేషన్స్ అనేవి నీకు ఉంటాయి అనమాట ఇన్ దిస్ పర్టికులర్ కబోర్డ్. సో దాన్ని డీల్ చేయడానికి లైక్ ద స్టడీ ఆఫ్ దట్, లేకపోతే దాని అకౌంట్లోకి తీసుకున్న స్ట్రక్చర్ డిజైన్ చేయాలి, బిల్డింగ్స్ డిజైన్ చేయాలి, అది తెలుసుకోవడం వీ షుడ్ నో అబౌట్ స్టెనో మెటీరియల్స్ అనమాట. సో స్టెనో యూనిట్ 1, 2, 3, 4, 5 మీకు తెలుసు ఆల్రెడీ ఏమేమి ఉన్నాయో. 1 and 5 పర్లేదు, ఈజీయే. 2, 3, 4 ఇస్ వేర్ పీపుల్ యాక్చువల్ డీటెయిల్ ఫ్రమ్ ద సబ్జెక్ట్ మన క్లాస్లో అయితే. సో 1, 5 ఐ విల్ టెల్ యూ, అండ్ 2, 3, 5 కూడా ఐ విల్ ట్రై టు మేక్ యూ గైస్ అండర్స్టాండ్. అయితే ఏం లేకపోలేదు, నాకు కూడా తెలీదు, చూద్దాం పద. సో దట్స్ ద బేసిక్ లైక్ అండర్స్టాండింగ్ ఆఫ్ స్టెనో మెటీరియల్స్, లైక్ ఎందుకు నేర్చుకుంటున్నావు ఏంటి అనేది. సో ఒక్క నిమిషం ఆగండి, ఇది ఓపెన్ అవ్వట్లేదు దీనమ్మ. దీనమ్మ సో యా, ఎవరు వచ్చాడు? ఏ హాయ్ గైస్, హలో. ఏం ఏం చేస్తున్నారు చదువుకోకుండా? నా స్ట్రీమ్ చూస్తున్నారు. అల్లికి అక్కడ పెడదాం, ఆగండి, ఇందాక పెడదాం అనుకున్నా, మర్చిపోయా. ఇన్స్టాగ్రామ్. హలో, హాయ్ హాయ్. ఇదిగో నాకు తెలిసిన అండర్స్టాండింగ్ నేను చెప్తున్నాను, నాది ఫాలో అయ్యి వెళ్ళకండి ప్లీజ్, ఎందుకంటే వెళ్ళొచ్చు, ఎందుకంటే నేను నాది ఫాలో అయితే వెళ్తాను కాబట్టి. బట్ మీ గుడిసిపోద్ది నాకు సంబంధం లేదు, అందుకే స్ట్రీమ్ పేరు కూడా అదే, గుడ్ అవుద్దా గుడిసిపోద్దా. ఐఎమ్ పుట్టింగ్ దిస్ సో హార్డ్. ఒక్క నిమిషం, అట్లా కోపేదో మూడున్నప్పుడు చూస్తుంది. అది ఏ యూనిట్ చెప్తున్నావా? మొత్తం చెప్దాం అనుకున్నాను. 6కి జిమ్కి వెళ్తా, సో 6 వరకు ఫ్రీ, ఇంకో 2 గంటలు ఎంత అయితే అంత. ఈరోజు మొత్తం ఎస్ఎం చెప్తా, నేను అనుకున్నా అంటే ఒకరోజు ఎస్ఎం, ఒకరోజు బిఎంసీపీ, ఒకరోజు ఈజీ. నాకు 3 ఉన్నప్పుడు 3 ఉంటుందో తెలియదు, చూద్దాం. అవి మిస్ అవుదా దెంగే అయితే కాల్ చేయి, ఇక్కడ ఎందుకున్నావు? మాకు ఇందాకే చెప్పేసి మా స్టీని చూడద్దమ్మా, బూత్లు వస్తాయి అంటే, ఎందుకు బూత్లు ఎవరితో మాట్లాడుతుందని చెప్పి అంది అనమాట. ఇదిగో ఇలాంటి వాళ్ళ వల్లే అది. సో 20 నుంచి విల్ స్టార్ట్. ఫస్ట్ కాన్సెప్ట్ ఆఫ్ స్ట్రెస్ స్ట్రెయిన్, విల్ స్టార్ట్ ఫ్రమ్ దేర్ ఓన్లీ. ఏం ఫోటోలు పెట్టాడు ఇది పుగ్గాడు. ఎక్కడున్నావు దగ్గరగా? ఇంట్లో తప్ప పెద్దగా ఉంటావే. యూనిట్ 2 నుంచి స్టార్టింగ్ కాదా, యూనిట్ 1 నుంచి స్టార్టింగ్. యూనిట్ 2 ఎవెన్చువల్లీ ఐ విల్ గెట్ దేర్. యా, బాల్లో ఉన్నావా? నైస్, ఎంజాయ్. సరే, ఐ విల్ గెట్ స్టార్టెడ్. సో ఐ డోంట్ థింక్ కొంచెంసేపట్లో మీ స్ట్రీమ్స్ వెళ్ళిపోతా అని చెప్పి నాకు అనిపిస్తుంది. వెళ్ళిపోయినా పర్లేదు, ఐ డోంట్ మైండ్, మీ ఇష్టం. బట్ డౌట్లు ఏమైనా ఉంటే పెట్టండి, నాకు పర్సనల్ మెసేజ్ చేస్తే పర్లేదు, చూస్తాను. సో ఫస్ట్ విల్ స్టార్ట్ స్ట్రెస్ అండ్ స్ట్రెయిన్. ఇలా అయితే నా బ్యాగ్ కనిపిస్తుంది, బ్యాగ్ బాగోదు, కొన్ని సైడ్ నుంచి నాకు. స్ట్రెస్, స్ట్రెయిన్. ఓకే, ఫస్ట్ విల్ టాక్ అబౌట్ స్ట్రెస్. స్ట్రెస్ అంటే యూజువల్ మనం తీసుకునేది. సో ఇప్పుడు స్ట్రెస్ అంటే లైక్ యూ గైస్ వాట్ నో బేసికల్ వాట్ స్ట్రెస్. స్ట్రెస్ ఇస్ లైక్ ఫోర్స్ బై ఏరియా. సో ఈ ఫోర్స్ అంటే యూజువల్గా ఫోర్స్ బై ఏరియా అంటే పీపుల్ యూజువలీ రిలేట్ స్ట్రెస్ టు లైక్ అంటే ఫోర్స్ బై ఏరియా సేమ్ యాజ్ ప్రెషర్. సో లైక్ మీరు యూనిట్ చూసుకుని సేమ్ యాజ్ ప్రెషర్ ఓన్లీ ఫోర్స్ బై ఏరియా అనేది, బట్ ఇట్స్ నాట్ ప్రెషర్ టెక్నికలీ. అంటే ఇప్పుడు నేను ఈ బాడీ పైన కొంచెం ఫోర్స్ అప్లై చేస్తున్నాను, కానీ నా చెయ్యి అనేది ఇట్స్ నాట్ గోయింగ్ త్రూ ద బాడీ. So there's an opposing force is acting on my hand, which is not letting me penetrate to the board. హలో చదువు చెప్తున్నా వింటావా బాయ్ బాయ్ వెళ్ళిపోతున్నావా ఎందుకు బై బై
ఏమిచ్చినా నాకు విషెస్ కుదరదు నా దగ్గర దొరుకుతుంది
బాల్ నీకే ఆడుకో రేపిస్తాను
మొన్న అమ్మవారి చీర మురళి అనే తెచ్చాడు కాశీ నుంచి అమ్మవారి చీర
యా సో ఎక్కడ ఆపాము యా సో ఒక బాడీ పైన మనం ఫోర్స్ పెడుతుంటే లైక్ ఈ బోర్డ్ అనేది లైక్ నా చెయ్యి దాని నుంచి వెళ్ళట్లేదు ఇఫ్ రిమెంబర్ లైక్ మెకానిక్స్ అండ్ ఆల్ వెన్ లైక్ నో ఏమంటారు లైక్ ఇట్స్ స్టాటిక్ కండిషన్ నేను ఎప్పుడైతే ప్రెస్ చేస్తున్నాను సో స్టాటిక్ కండిషన్ నీకు ఫోర్సెస్ అనేది జీరో రావాలి సో జీరో అంటే ఇప్పుడు లెట్స్ టేక్ దిస్ as హారిజాంటల్ ఫోర్సెస్ సో నేను ఒక ఏ ఫోర్స్ అప్లై చేస్తున్నా ఈ బోర్డ్ పైన ఆ బోర్డ్కి తిరిగి ఒక ఫోర్స్ అప్లై చేస్తుంది టు అపోజ్ మై హ్యాండ్ యా సో నా హ్యాండ్ని అపోజ్ చేసే ఫోర్స్ ఏదైతే ఉందో దట్స్ కాల్డ్ స్ట్రెస్ అనమాట సో స్ట్రెస్ ఇస్ బేసికలీ అన్ అపోజింగ్ ఫోర్స్ యాక్టింగ్ ఆన్ external loads basically. So that's called as stress. ఈ స్ట్రెస్ అనేది బాడీ ఇండ్యూస్ చేస్తుంది అండ్ బేస్డ్ అపాన్ ఆ బాడీ ఎంత స్ట్రెస్ తీసుకోగలదు అని చెప్పి మనము స్ట్రక్చర్స్ అనేవి డిజైన్ చేస్తాం అనమాట లైక్ మనము టెన్షన్ టెస్ట్ చేసాం కదా ఎస్ఎంలో బేస్డ్ ఇట్స్ రిలేటెడ్ టు దిస్ ఓన్లీ అనమాట లైక్ స్ట్రెస్ అని తీసుకుంటుంది దాన్ని బట్టి కనిపిస్తుంది అసలు క్లియర్గా అక్కడ ఏదో అలా కనిపిస్తుందిలే కొంచెం పెద్దగా ఏం ట్రై చేస్తా కొంచెం పెద్దగా స్ట్రెయిన్ కనిపించింది ఇది ఇది కొంచెం బాగా అనిపిస్తుంది అయితే కంటిన్యూ చేద్దాం సో స్ట్రెయిన్ ఇప్పుడు స్ట్రెయిన్ అంటే ఏంటంటే లైక్ ఐ టాక్డ్ అబౌట్ హౌ ఒక బాడీ పైన ఎప్పుడైతే ఫోర్స్ అప్లై చేస్తున్నామో అది తిరిగి ఒక అపోజింగ్ ఫోర్స్ అప్లై చేస్తుందని చెప్పి వీ టాక్డ్ అబౌట్ కానీ ఇట్స్ నాట్ లైక్ ఇట్స్ నాట్ లైక్ దట్స్ ద హోల్ థింగ్ ఇట్స్ హ్యాపెనింగ్ ఎప్పుడైతే దీనిపైన ఫోర్స్ అప్లై చేస్తానో కొంచెం డిఫార్మేషన్ ఆల్సో టేక్ ప్లేస్ అనమాట అంటే బాడీ అనేది నా చేతిని కంప్లీట్గా లైక్ ఇట్స్ నాట్ అపోజ్ దేర్ సమ్ మైనర్ డిఫార్మేషన్ విచ్ టేక్ ప్లేస్ విత్ ఇన్ ద బాడీ ఇక కనిపించదు ఇట్స్ బికాస్ రియల్లీ మైనర్ డిఫార్మేషన్ బట్ ఇట్ విల్ హ్యాపెన్ అనమాట ఇట్స్ మచ్ మై ఎవిడెంట్ లేకపోతే ఇది కొంచెం గట్టి ఈ వుడ్ కొంచెం గట్టిగా ఉంటుంది కాబట్టి యూ వాంట్ ఫైండ్ ఇట్ హియర్ అలా కాకుండా ఇప్పుడు బేసిక్గా అందరూ తీసుకునే ఎగ్జాంపుల్ రబ్బర్ బ్యాండ్ ఐ టేక్ దాట్ ఓన్లీ సో రబ్బర్ బ్యాండ్ ఎప్పుడైతే ఫోర్స్ అప్లై చేస్తావు ఇట్లా ఎలాంగేట్ సో ఎంత ఎలాంగేట్ అవుతుంది లెట్స్ ఇట్స్ ఎలాంగేటింగ్ డిస్టెన్స్ ఆఫ్ డెల్టా ఎల్ సో డెల్టా ఎల్ డివైడెడ్ బై ఒరిజినల్ లెంత్ ఆఫ్ ద బాడీ ఇస్ నోన్ యాజ్ స్ట్రెయిన్ అనమాట సో దట్స్ ద కాన్సెప్ట్ ఆఫ్ స్ట్రెస్ ఏదో చేస్తారు బట్ అండ్ కాన్సెప్ట్ ఆఫ్ స్ట్రెయిన్ సో ఈ స్ట్రెస్ స్ట్రెయిన్ బట్టే మనము లైక్ దిస్ ఇస్ ద బేసిస్ ఆఫ్ యువర్ హోల్ ఎస్ఎం అనమాట సో ఈ స్ట్రెస్ స్ట్రెయిన్ బట్టే మనము తర్వాత వీ విల్ డిస్కస్ వేరియస్ థింగ్స్ లైక్ ప్రిన్సిపల్ స్ట్రెస్ ప్రిన్సిపల్ స్ట్రెయిన్ యూనిట్ 5లో వస్తుంది తర్వాత ఎస్ఎఫ్డి పిఎండి కూడా అక్కడ షియర్ ఫోర్స్ డయాగ్రామ్ తర్వాత ఈ యాక్ట్ అయ్యే అదే షియర్ ఫోర్స్ డయాగ్రామ్ బెండింగ్ మూమెంట్ డయాగ్రామ్ వల్ల యూ కెన్ ఫైండ్ ద లైక్ ఆ బాడీ ఎంత డిఫార్మ్ అవుతుంది అంటే ఎంత స్ట్రెయిన్ ఇట్స్ అండర్ గోయింగ్ ఎంత స్ట్రెస్ అని డెవలప్ అవుతుంది బాడీలో అదంతా బేస్డ్ అపాన్ లైక్ కొన్ని ఫ్యాక్టర్స్ వల్ల విల్ ఫైండ్ అది ఫ్యూచర్లో వస్తుంది సో దిస్ ఇస్ ఆ బేస్ ఆఫ్ స్ట్రెస్ అండ్ స్ట్రెయిన్ అనమాట నెక్స్ట్ ఏం టాపిక్ ఉంది సెయింట్ వర్నర్స్ ప్రిన్సిపల్ స్ట్రెస్ అండ్ స్ట్రెయిన్ డయాగ్రామ్ ఇది ఈజీ ఓన్లీ చెప్తాం కొంచెం మిడిల్ పెట్టుకోండి బెటర్ ఫక్ Okay, next is Saint Vernet's principle. Spilling bokkale. Saint Vernet's principle basically I'll tell in words only. Like it's not that big of a topic. మీకు వస్తే 2 మార్క్స్ లెక్కన రావచ్చు కానీ బేసిక్ ఏమంటుందంటే లెట్స్ ఇప్పుడు ఇది ఒక బాడీ ఇట్స్ హ్యాంగింగ్ బై ఇట్స్ ఓన్ సెల్ఫ్ వెయిట్. సో దాని సెంటర్ ఆఫ్ మాస్ నుంచి ఒక ఎంజీ ఫోర్స్ లాక్ట్ అపాన్ ఇట్. సో బేసిక్గా ఏమంటుందంటే ఎట్ ద లైక్ ఎక్కడైతే ఫిక్సెస్ ఉందో ఈ ఫిక్స్డ్ అనే దగ్గర ద బాడీ విల్ హ్యావ్ మోర్ డిఫార్మేషన్ కంపేర్ టు ఫ్రీ ఎండ్ అనమాట. దట్స్ బేసికలీ సెయింట్ వర్నర్స్ ప్రిన్సిపల్. ఐ థింక్ ఒకసారి క్రాస్ చెక్ చేసుకొని సాగండి. Yeah. So a better way of explaining this is like at the end where it's fixed, అక్కడ నీకు లైక్ దిస్ ఎక్కడైతే ఫిక్స్ చేసి ఉందో లైక్ లెట్స్ సే ఒక వాల్ విచ్ ఇట్స్ ఫిక్స్డ్ వాల్ కానీ సమ్ సీలింగ్ ఏదో ఒకటి. సో అక్కడ లైక్ ఇట్ విల్ ట్రై టు హోల్డ్ ద బాడీ కాబట్టి దేర్ యూ విల్ హ్యావ్ మోర్ ద స్ట్రెస్ డెవలప్మెంట్ ఇన్ ద బాడీ అండ్ హెన్స్ మోర్ ద లాంగేషన్ ఆల్సో. సో ఒక్క నిమిషం. So most stress development and take place at the like ends with fixed compared to the rest of body. Like ఇప్పుడు ఈ బ్లూ కలర్ షేడ్ రీజన్ ఉంది కదా, ఇక్కడ because it's fixed, it tends to elongate more there compared to like let's say in somewhere in the middle. That's Saint Vernon's principle. అనిపిస్తుందా మళ్ళీ లాడాలా ఉంది. పెట్టదు. తీసి పెట్టదు కొంచెం. కూర్చొని చెప్పాలి ఇప్పుడు. చేదు బొక్క కింద పడదు. అమ్మా సరే నెక్స్ట్ ఎక్కడ హ్యాపెన్ సెయింట్ వర్నర్స్ ప్రిన్సిపల్ కదా, అది అయిపోయింది. నెక్స్ట్ చెస్ స్ట్రెయిన్ డయాగ్రామ్. ఇది కూడా విల్ హ్యావ్ లుక్ ఓవర్ ఇట్. నిన్న ఈరోజు ఎస్ఎంఎస్ ఎగ్జామ్ జరిగింది కాబట్టి యూ హ్యావ్ మోర్ ఐడియా అబౌట్ దిస్, బట్ స్టిల్ విల్ గో ఓవర్ ఇట్. ఏది డయాగ్రామ్ తీసుకున్నాను యా. సో ఇప్పుడు దిస్ ఇస్ మై ఇది స్ట్రెస్ y-axis I'm taking stress, x-axis I'm taking strain. So this is for the mild steel material. Okay, So this is the mild steel material which I am taking stress and strain for. సో మైల్ స్టీల్కి when I am ఒక స్ట్రెస్ స్ట్రెయిన్ లైక్ ఎంత స్ట్రెస్ తీసుకుంటే స్ట్రెయిన్ తీసుకుని ఒక గ్రాఫ్ గీసా అనుకో ఇట్ విల్ ఎండ్ అప్ సంథింగ్ లైక్ సో దిస్ ఆర్ స్ట్రెస్ వర్సెస్ స్ట్రెయిన్ గ్రాఫ్ మరి ఇంత డిప్ రాదు బట్ దట్స్ బెటర్. సో లెట్స్ సే దిస్ పాయింట్ ఓ ఆరిజిన్, ఇది ఏ, దిస్ బి, దిస్ ఇస్ సి. ఇది కాకుండా ఒక డాటర్ గ్రాఫ్ గీస్తాను, బ్లూతో గీద్దాం. సో ఇట్స్ సంథింగ్ లైక్ లేదు, ఓకే అది పైకి అవుతుందా? ఇంత లాడాల క్లారిటీ ఉంది చూడు. ఓకే యా, సో దిస్ మైల్ స్టీల్ అనమాట. సో ఇప్పుడు ఈ పాయింట్ ఏబిసి అండ్ డాటెడ్ గ్రాఫ్ గురించి డాటెడ్ లైన్ గ్రాఫ్ గురించి మాట్లాడుకుందాం. సో ఈ పాయింట్ ఏ అంటే ఏంటంటే దిస్ అ ఈల్డ్ పాయింట్ అనమాట. ఏ వచ్చేసి ఈల్డ్ పాయింట్ అండ్ బి వచ్చేసి మ్యాక్సిమం లోడ్ అండ్ సి వచ్చేసి ఇట్స్ అ రప్చర్ పాయింట్. మ్యాక్స్ లోడ్ అని రాయొద్దు, మ్యాక్స్ లోడ్ అని రాద్దాంలే ఉంది ఒక్క. సో ఇప్పుడు ఏ అనే ఈల్డ్ పాయింట్ అంటే ఏంటంటే లైక్ ఈ పాయింట్లో లైక్ దీనికి మించిన స్ట్రెస్ ఎవరు వచ్చేది, హూ ఇస్ ద గ్రేట్, ఎవట్రా నలుగురు ఉన్నారా? ఇట్స్ ఓకే, ఐల్ కంటిన్యూ. Yeah. Hey, Balaji, I didn't expect you to come. Hi, Balaji. How are you, Balaji? Love you, Balaji. But it's okay, I'll continue. So, here's yield point. So, what happens is because you can have to switch to English louder. Okay, so, O నుంచి A వరకు లైక్ మన స్ట్రెస్ స్ట్రెయిన్ ఇట్ వేస్ లీనియర్లీ అనమాట. అంటే ఇక్కడ మీకు డిఫార్మేషన్ విచ్ టేక్స్ ప్లేస్ ద బాడీ హ్యాస్ ద ఎబిలిటీ టు కమ్ బ్యాక్ టు ఇట్స్ ఒరిజినల్ పొజిషన్. సో yeah, it has the ability to come back to its original position. కానీ ఈ ఏ పాయింట్ దాటి when it goes to బి లైక్ ఏ పాయింట్ దాటిన తర్వాత you'll get like ఏ దగ్గర ఇట్స్ ద yield point where the బాడీలో ఒక మైనర్ డిఫార్మేషన్ అని ఉండిపోతాయి అనమాట. లైక్ అదే ఆ స్టీల్ రాడ్ అండ్ యూటీఎం ఎగ్జాంపుల్ తీసుకోండి. అప్ టు 0 నుంచి ఏ పాయింట్ వరకు వెన్ ఎవర్ ద లోడ్ ఇస్ అప్లైడ్ ఆన్ ద స్టీల్ రాడ్, లైక్ ఎప్పుడైతే మనం యూటీఎంలో లాగుతుంది కదా, సో అక్కడ మీకు డిఫార్మేషన్ వాట్ టేక్స్ ప్లేస్, ద బాడీ హ్యాస్ ద ఎబిలిటీ టు కమ్ బ్యాక్ టు ఇట్స్ ఒరిజినల్ పొజిషన్. కానీ ఆఫ్టర్ yield పాయింట్ మీకు చిన్న చిన్న మైండ్ డిఫార్మేషన్ వస్తుంది, ద బాడీ ఇట్ గాట్ డిస్ప్లేస్డ్ అండ్ దట్స్ యాక్ట్ పర్మనెంట్ ప్లేస్మెంట్ అనమాట. ఇట్ వోంట్ కమ్ బ్యాక్ టు ఒరిజినల్ పొజిషన్. దీని తర్వాత బాడీ స్టార్ట్స్ యాక్టింగ్ ప్లాస్టిక్ మెటీరియల్, అంటే నీకు మైండ్ డిఫార్మేషన్ కానీ ఇట్ స్టార్ట్స్ బికమ్ పర్మనెంట్ డిఫార్మేషన్స్. సో ఇట్స్ దిస్ హౌ ద స్ట్రెస్ ఆఫ్ స్ట్రెయిన్ గ్రాఫ్ విల్ అక్కడ అనమాట. ఈ స్ట్రెస్ ఆఫ్ స్ట్రెయిన్ ఇఫ్ యూ టేక్ లైక్ ద స్లోప్, ఆ స్లోప్ వచ్చేసి ఇట్స్ యువర్ అదే యంగ్స్ మాడ్యులస్. ఎస్. సో స్లోప్ వచ్చేసి యువర్ యంగ్స్ మాడ్యులస్. ముగ్గురు ఉన్నారు, వన్ ఇస్ బాలాజీ, వన్ ఇస్ మీ ఓన్లీ. హూ ఇస్ అదర్ వన్? I don't know. It's okay. Continue. Yeah. So slope వచ్చేసి it's యంగ్స్ మాడ్యులస్ అనమాట. సో స్లోప్ అంటే ఏంటి? ఇట్స్ యువర్ dy dx or it's your stress by strain. So stress by strain is equals to Young's modulus, which is denoted usually by E. పర్లేదులే. సో యా, సో ఇప్పుడు డాటర్ గ్రాఫ్ అంటే ఏంటంటే ఇప్పుడు స్ట్రెస్ స్ట్రెయిన్ అని చెప్పి అనుకుంటున్నాం. ఇక పక్కన అర్థం ఇప్పుడు E ఈజ్ ఈక్వల్స్ టు స్ట్రెస్ బై స్ట్రెయిన్. స్ట్రెస్ స్ట్రెయిన్ వాల్యూస్ ఎప్పుడైతే మనం సబ్స్టిట్యూట్ చేసుకుని ఇట్స్ F by A into the whole thing మళ్ళీ డివైడ్ బై డెల్టా L డెల్టా బై ఎల్. డెల్టా అంటే మైనర్ డిఫార్మేషన్స్ అనుకున్నాము. విచ్ ఇస్ ఈక్వల్స్ టు ఎఫ్ఎల్ బై ఏ డెల్టా ఈ అనేది. సో ఇప్పుడు ఏంటంటే మనకి అవర్ స్లోప్ విచ్ ఇస్ యంగ్స్ మోడల్స్ ఇట్ డిపెండెడ్ అపాన్ ఎఫ్ఎల్ బై ఏ డెల్టా. సో ఏతో ఇట్స్ ఇన్వర్స్లీ ప్రపోర్షనల్ అనమాట. సో ఇప్పుడు మనము ఎప్పుడైతే లైక్ ఫర్ మైండ్ స్టిల్ వెన్ యూ స్టార్ట్ లైక్ పుల్లింగ్ ఇట్ దేర్ మన నెక్ ఏరియా ఏదైతే ఉంటుందో ఇట్ స్టార్ట్స్ గెటింగ్ రెడ్యూస్డ్ అనమాట. సో బికాస్ ద నెక్ ఏరియా గెట్స్ స్టార్ట్స్ గెటింగ్ రెడ్యూస్డ్, ఈ ఏరియా కాంపోనెంట్ అనేది ఇట్ స్టార్ట్స్ గెటింగ్ రెడ్యూస్డ్ అనమాట. సో ఏరియా తగ్గే కొద్దీ ఎక్స్ మోడల్ ఇస్ ఇంక్రీజింగ్ అనమాట. Like okay, your force also increasing, but your area is increasing at a much higher rate compared to your force. So అందుకే మనకి ఈ స్ట్రెస్ స్ట్రెయిన్ గ్రాఫ్ you look at a higher slope అన్నమాట. So that's your dotted graph. సో dotted graph అంటే లైక్ మనకి మామూలు గ్రాఫ్ ని చూసుకుంటే దిస్ ఇస్ అవర్ మ్యాక్స్ లోడ్, బట్ ఇన్ dotted graph your max load is much higher than your actual graph అన్నమాట. So usually these points are used to like design any steel structure or using mild steel. So this is about stress strain graph. Next వచ్చేసి, so that's the actual graph. No, the black one is the actual graph. The blue one, yeah, you can take it like that. The blue one is the actual graph. Like taking in consideration the decreasing area, if you draw, you'll get this. But it's very hard to find a decreasing area. Like you can't place your hand there because there's production of heat there. Because yeah, like the body is getting ruptured, so like the energy is getting released, so there's production of heat also. Like the energy which is like the strain energy which is developed in the body, it's released in the form of heat and later sound. So you can't actually measure the neck area, like how it's like the rate of it's decreasing. Usually how it's done is yeah, you got it. I'm just yapping about it, but it's okay, let me continue. Should I just do it in English? I feel comfortable in English. I don't know why. What do you say? Why am I? Because you taught me only. What? So many days. Oh yeah. I don't know. I just feel comfortable in English compared to Telugu. I guess it's okay. My stream, my wish. I'll continue in English. So yeah, that's about your stresses and strain graph. So blue one again. Everything is all. Now we'll look at stress strain graph for some other materials. I'll just draw it. So let me just draw it. So again, this is the stress, this is a strain, and if for various for other materials, if I draw, should I just show it? I think that's better than me drawing. Let me show. Yes. This is for other materials like concrete, aluminum, cast iron, and high carbon steel. So with these materials, like you don't see that such a like wide graph. Like for the mild steel, you saw such a like wide graph over the huge span. But for this, you see the graph suddenly ending at a point. So this is because that these are the compared to like your mild steel, these are brittle materials. So they have a sudden rupture. Like at a point, they have a tendency to collapse suddenly, compared to steel, which tends to yield before collapse. That's called collapse as failure. I think that's a better way to indicate it. So these have a tendency to to have fail immediately, whereas steel it tends to yield before the failure. Yield basically means it undergoes elongation. So yeah, so that's your stress and strain graph for various materials. There's something else called proof stress. Let me explain that also. Like proof stresses, okay, for the like usually it's important for us to find a yield point so that we can know from where the material starts acting plastic. So for this you have actually defined a dipper, so it's easy for us to find a yield point. But whereas for these materials, let it focus it. Yeah. So for fucking hell. Yeah, so for these materials you don't have a like defined dip for it. Like there's a sudden rupture. So you should know a point of somewhere that it starts acting like a plastic material. So for that there's something called proof stress. What you do is yeah, you take a 0.2% offsetter and you draw you draw like an offset line. So you draw you project this offset line onto the graph as a tangent. So where this wait a minute. Sorry. I told it reverse. So first, what you do is you draw a tangent to the curve which you get, and from that tangent you project it at a distance of 0.2%, and where this 0.2% of stress it interacts with the graph of the stress strain graph. That's usually your yield point. So that's the point where you can say that rupture takes place, or not rupture, the plasticity of the material starts. It's not like different for all the materials, but this is one of the materials from which you can design structures based with for these kind of materials. So yeah, what's the next topic? By the way, thank you Balaji for staying so long. I didn't expect anyone to actually show up, so I appreciate you being. I think you're here still because it shows three viewers. One is me only. One of one I'm thinking is you. The other one I don't know. Next, the whole volume, like the whole chapter is boring as fuck, man. Like for me, for teaching us, it's boring as fuck only. SFD BMD is where the shit gets interesting. I just want to get started with it, but it's okay. I'll follow some manner to it. Hmm. Sure, I completed this factor safety lavadana కోసం లేదు. Okay, I'll get started with the poison's issue and all. Uh, yeah, sure. Where is this? I don't know for what we kept yes, but okay. Yes, I agree with you. Okay. Poison's issue. Let me draw a diagram for this. Look at me exchanging between markers like a pro. I don't know. I feel like PhD doing all of this shit, which not a bad thing to be honest. Yeah. So let's talk about poison distribution. Uh, let okay. We'll take it as a beam only. It's cantilever beam because it's fixed on one end and free on the other end. So let's say I'm applying a load P. I'm pulling it with a load P. I think it's I don't know what's the specific reason for 0.2%, but I think it has been like through experimental data they have found that taking an offset 0.2% is good enough for designing it. Like you can say like it's a factor of safety basically. This 0.2% limit. Under that it's like permissible limit in the experiments. But taking an offset more than that tend to the failure of the material. Okay, I'll come in a minute. Nice. Back to zero viewers, I guess. Yes. So Poisson's ratio. Yeah. So let's say this beam is being pulled with not, it's not technically a beam. Let's say bar only. It sounds better. The bar is being pulled with a force of P. So usually, from what we see, like logically, if you think, the elongation should in the bar should occur along its length, but not its width. So let's say this is the length, and this is its width. Let's say it's some B. So it makes sense for the bar to elongate along its length, but not its width. But what happens is, as it's elongating along, like as it's pulled along its length, the bar it elongates, like it deforms both along its length and its width. Like this blue color graph is how it actually like elongates. So you can see there's a deflection in both delta L and both delta B also. So this is basically Poisson's. Poisson ratio basically is to find like how much, like it's to establish a relationship between a delta L and delta B. So for this, how we can actually write it is, let's say mu is your Poisson's ratio. Mu is usually equal to minus is because that because see, here breadth is decreasing as length is increasing. So you indicate this like it's inversely proportional. So you indicate that with a minus is elongation traverse direction divided by elongation in x direction. So traverse being the elongation, sorry, not elongation technique, it's because it's decreasing, but still, for the sake of it, I'm just calling it elongation, bear with me. So elongation along traverse direction divided by elongation under the normal x direction, like this is your x, and elongation along any other axis, just traverse, like let's say y, and yeah, like instead of it's like width along its breadth also it does. Why does it show one person? I have no fucking clue. For me, it shows two. I am watching one more thing, and I think you are watching. But yeah, it feels good to know there's someone watching, because before there was like zero viewers. I was like, why am I doing this? I can do all of this alone. But okay, motivation, I guess. Let's continue. Now it shows three people. I don't know who the third person is, but let's continue. So yeah, so traverse direction basically means along y or along x, but like not x and y. I can take any oblique plane also. Like instead of y, I'll take instead of y I'll take an axis along like 45 degrees, I guess. Along 45 degrees also you can find using like Mohs cycle and all, which comes later on. So along that also I can find Wasser load, Wasser stress and all. So that also can be at oblique plane only. So that's also comes to traverse direction only. But yeah, so this Poisson ratio is usually elongation of traverse direction by elongation under the x, and minus I already told you, because here length is increasing but your breadth is decreasing. So that's the bias is to indicate the like opposing nature of, like the inverse nature of it. Yeah. So in taking this in x and y, you can denote it as elongation y is equals to elongation in x is equals to, sorry, elongation z, sorry, because z I'm taking as a traverse and x I'm taking as the actual direction, minus of mu elongation x. So this is how I can, sir, this one shot. I I'm thinking of it like that. I don't know. 6 o'clock I'm going gym. So up to then how much I can complete I'll do. And later at night, if time permits and I have the mode, I'm thinking of completing the whole 5 units. I mean I only have 5 units. So yeah. Is this a one shot? Ask your mom. Okay, no, your mom jokes. Let me cut. I, why did I go there? It's okay. Let me continue. So yeah, so this is a Poisson's issue. This is about Poisson's issue, but this Poisson's issue I have only taken under like x and y axis. You can also include like, sorry, I have taken it as like the low. It's being pulled only in like x direction. You can also take it as let's say the body like this, and I'm pulling it along px, and I'm also pulling it along py. So x will also affect y will also affect x. So you can form a relationship between both as such. So let's say elongation x can be written as like the net elongation. This is, can we written this? Wait a minute. Yeah, it can be sigma x by E. Sigma x basically is the stress and extra action divided by E is your the Young's modulus minus mu of sigma y by E. Yeah, so this is the actual component because of px, and this is the component of elongation because of py. Same thing you can write for the y also as sigma y by E minus mu of sigma x by E. Yeah, you can also take it to treat and include a sigma x component also if you want. Do it if you want. Yes. Okay. Is this clear, Balaji? I'm just making sure that you're here. It motivates me. Are you here? Nice. Blue's not responding. Oh, yes. Hi. Let me continue then. We are done with poison's issue. How much lag is there, by the way? Like between me saying and you actually hearing it. I wanted to see. Nice. Bro left, I guess. I don't know. It's okay. I'll continue. Hmm. Okay, there's you have EG with relationship and stress strains, like sorry, temperature stresses. Let me just go to it. It's okay. Oh, there's also type of stress and type of strains, but I really don't want to get into it because it's all theoretical and I fucking hate theory. I mean, it's interesting theory only, but still, I don't want to get into it. Let me see how what I can do. Yeah. Yes, a lot. What do you mean by a lot? Lag so bad, bro thought I was gone. No, no, it showed me one viewer there. That's why I was like, okay, maybe this guy left. So yeah, should I tell you about shearing strain? Should I? I'll just explain it here. I don't want to draw and all. See, basically shearing strain. I think you can see. Yeah, like basically like so far you have seen strain like along like tensile direction. This like strain you had like you have seen like normal strain like along its like length. But this is like you can say it's like kind of like an angular deformation because the body is changing along its like there's an angle at which the body changes. You can basically understand it, understand it by taking a experiment using a book. See, look at this book. Like if I'm pulling it along like its lengthwise, then you can say like that's your normal strain. No? But I'm keeping it like this. How should I show? Like yeah, and see I'm applying a force along its body, so there's an kind of like an angular deformation like towards the side of it. So that is your shearing strain. So yeah, your the shearing strain can be like represent like this is your shearing strain and this p divided by this x. Yes, that's the same reason I'm giving the same example. From then on, like, whenever people asked, I gave the same example because PhD gave it. Yeah. Yeah, so your shearing strain can be represented as a stress can be represented as P by LB. P is the force and L by LB is the area of it. Yeah, L and B. And your the strain due to like your shearing stress can be is denoted usually as gamma, and 2 by gamma is same as your stress by strain, which is H modulus. Yeah. There's also compressibility equations and all. So. I fucking hated this shit when I'm doing it. I should explain this or no. It's okay, I'll explain it. I'll explain the gist of it because I already know about it. It's okay. Come. So let me take two materials. We can find the strength of this materials. That's why the name strength of material. Okay, now. So let's say there's a composite material. Composite material basically means it consists of like two different materials. This black, let's say one material is this black shaded one, and one more is the blue shaded. Yeah. So okay. Well, let's say for black, I'll write it using black only. Let's take it this as one and this as two. So for one, we will say I'm taking length of both as the same, and what the water purpose actually change. I'm taking the area also to be same. Not, I'll take it as varying areas. I think that will be more. Let Let's say the cross section area of the first material is A1, and the second one is A2. Oh my God, he said. Yeah. And the Young's modulus of the first material being E and like E1, see, black, E1, and the second one being E2. So you can write two equations for this specific. Are you able to see E1 and E2 by the way? Like, is it clear enough for you to actually understand? It's like E1 and E2. Otherwise, I'll write it a little bigger. I'll wait for your response because it's a lag. No, okay. I will increase this material one. I'll try to this material one, and it's elastic. Like modulus of elasticity is E1. Yeah, I'll try to write here. E1 and it's area of cross section is A1, and this is material 2, and its elasticity, like sorry, its Young's modulus is E2, and its area of cross section is A2, and length I'm taking is constant. So let's say a load of P is acting on it. I should write it because like for me it's fine only, but for you guys who are watching, not you guys, you guy who is watching, it can be hard to see. So a load of P is acting. Fucking hell, black on black. Blue on black was more worse. It's okay. A load of P is acting downwards. Understand? So because of load P is acting, for the, let's say like because they are different materials. Okay, only sure. Then I'll continue. Because they are different materials, the stress produced in each of them will be different. So to find to find that, you need compressibility equations. So basically, you can take two equations for it. See, because they both a composite material, when load is applied, how much material one is deforming, material two should also deform by the same. Like because they both are attached, and the one more reason why it happens is look at the boundary of it. Like they both are attached to each other. So I'll draw it down here. This is the black one, and this is the blue one. See, as the blue one tries to move down, because of like the force like in the boundary, it tries to push like the black one also down. So they both like attached to each other. So under normal conditions, under like no failure conditions, as blue moves down, black also moves down along with it, and there's no like mismatch in elongation between them. So that's why we can take elongation in material 1 is equal to elongation material 2. So I'm taking elongation material 1 as sigma 1. It should be equal to sigma 2. Okay, I'll set more like this. Yeah, so sigma 1 should be equal to sigma 2. So sigma 1 I can write it as it's basically elongation. So elongation I can relate it using smallest like in this manner. Yeah, this visible only, no. E is equals to PL by A delta. Delta being not delta, I'll do it by sigma only. Sigma, so I think it's called sigma. Fuck it, anything. Sigma. So sigma is equals to PL by A E. So yeah, this is the equation which I'm going to substitute here. So P basically is force. Again, we wait a minute. Like force, it's acting on. We don't know like how much force each of it is taking because delta only anything is fine. Like my wish. Who are you? So we don't know how what's the stress which is being produced by it. So let it be. So for let's say the force taken by metal one is P1 and force taken by metal two is P2. That's actually one more equation we can write. I let it here only. Wait. This is equation one, huh? And equation two is force. The net force is equals to force taken by P1 plus force taken by P2. Like using these both, we can find the stress developed in both the bodies. So yeah. So let's say delta 1 delta 2, I can expand this equation like in such manner: P1 into L is constant, so I'll let L only by A1 into E1. I should write a little bit. A1 into E1 is equals to P2 into L by A2 into E2. So L and L are constant, so I can take L's out. That's what I do in life. I take the L's out, only W's in the moment. Okay. So P1 by A1 is equals to P2 by P1 by A1 E1 is equals to P2 by A2 E2. This is one equation and this other equation. So using these both, you can find what is P1, what is P2. P1 by A1 is stress developed in the material 1, and P2 by A2 is stress developed in material 2. I don't want to go more into this because I fucking hate this shit. Basically, this is called a compressibility equation. Comp equation. Haha, it stinks because you know comp and all. I am weird as fuck. Yeah. But you should be, bro, this is common sense. It is common sense, but you know what people say. Common sense is not so common. But yeah, that's the reason I'm saying. But see, I'll tell you one application of common sense here also. See, because if both meters are attached to each other, we can take sigma is equal to sigma 2. But let's say they're not attached to each other, but they attach to some not third party or what? Like attach some other material, kept it end to end. Yeah, end to end. Yeah, see, Balaji, you're toppers. I know you know. Yeah, end to end is, let's say they kept end to end. For people who don't understand what's end to end, let's say this is the black one and there's the blue one. Black one, BBC, and this avatar cock. I guess never mind. Why? Yeah. So they kept end to end and then they are like compressed. Let's say this is P, here also it's P. So in this condition, if you see, because it's being compressed, the P and P, like the loads are like P1 is equals to P2, but your elongation might not be the same because they are kept end to end. So in these kind of conditions, your the equation will switch. Like P1 is equals to P2, but your sigma 1 plus sigma 2 is equals to net sigma. You should form the equations based upon the condition. Just because it's a composite equation doesn't mean all everywhere these equations are valid. You should look at it. One, instead of keeping it end to end, there's also one more example which I can take, which is a nut and bolt. This is example which sir took in class. That's why I'm taking. I took this. Like yeah. So gray one is steel and the copper colored one is copper. Who could have thought? And it's covered by like on this end and this end it's like what do you say, a wooden plate is kept. So what happens is here, like the wooden plate is connected to a nut bolt. Like as the nut bolt turns, the wooden plate it goes down. It's thus acting force on the steel plate, the steel bar and the copper bar. So when the bolt is turned, the wooden bar, like the bar goes down, and the stress is developed in both the steel and copper. So here again, because it's a like they're not connected to each other. It's just a plate which is pushing both of them down. So because it's pushing both of them down, the force acting on both of it might be same, but the what do you say, the delta might not be the same. That's what I wanted to say. Wait, is it the same? Wait, did I say it wrong? Let me see. No, never mind. The delta will also be the same because if yeah, if delta is not the same, the wooden like the wooden plate will have dense. Yeah, delta will be the same, but your force will also be the same. Now the force will be opposite. Wait, let me think. No, that's this was the same condition as this one. Never mind. I thought it is a different case, but no, it's the same case. You should, yeah. I think end to end is the example I can take. I can't remember any other examples. Okay, we'll continue. Now we have temperature stresses. My laptop is running out of charging. How much is that? 10% is that. We'll see. I at least want to complete unit one before they close this. Unit two I can do at night, later at night. Unit two is the main thing, because many people in my class are struggling with unit two only because many less people know about SFD, BMD and all. So that's my main focus. I mean, it's not like I don't think they'll watch this completely because, yeah, I don't think they'll watch this because I don't know why would they see me ranting about all of this shit. But still, we'll continue. I don't know why you are watching. I don't. I don't know why you are watching because it's not there for you. Your exam also over, but still, I appreciate you watching. Why are you talking about attention span? You are the last person who should be talking about attention span and all. Makes sense. You're bored as fuck. I have been watching Better Call Saul. I stopped it for like a month. I don't know why. I just gave it a break and I started watching it like from yesterday. It's really good. I completed it off. I think. Okay. So after this temperature stresses, I don't want to stress a lot on it. So, but I just say what's the gist of it. So when let's say there's a bath. So let's say it's not it's a very bad looking bath, but still bear with me. So let's say this bar is like heated. Okay, the bar is being heated. Because the bar is being heated, like when things get heated, they tend to expand. So like, shoot, wait, why am I losing my mind? Yeah, when things get heated, they tend to expand. You know why they expand? I don't have to explain you all of that shit. So they tend to get expanded. So when they expand, let's say it's left on a frictionless surface. I'm taking a this is a frictionless surface. It's mu is equals to 0. So because it's frictionless surface, the body can expand without taking any opposing forces. So because not taking any opposing forces, there's no stress development, there's no nothing. But let's say instead of it being on a frictionless surface, the body will take temperatures rising. Let's not put temp actually. Temperature rising, but the body is enclosed within a box or something. Like it's enclosed in a box which doesn't allow it to expand. Because it's not allowing it to expand even though the temperature is rising. Now there's stress development within the body because the body itself is expanding. Like the L is increasing. Like it increases by a minor amount only, but still that also will be able to will calculate. So as its elongation is being resisted, there's a force acting on the bar. So this temperature stresses. Do you have a yield of the ends also? Meaning, like the ends means like the box it's being enclosed in. Do you mean that? 0.2 mm. I mean, you can never. I don't know how much it along. It depends upon temperature. Depends on the material of the body. It tends to elongate. I can't say it's like 0.2 mm or something. Depends upon what's happening there. I didn't get your question by the way. Can you like frame it better? I mean, the ends will also move by fixed amount. What ends? Like you're okay. Let me. You're talking about the shade them in blue. You're talking about those ends. Oh yeah, I mean in a general condition, yes, you can take both of it. Like let's say this material one and this material two. So this will have a different coefficient of expansion. This will have a different coefficient of expansion. So they will vary by a different amounts. So again for this also you can write compatibility equation same as the previous case. So yeah, that problem will also arise, but in the structures we use or we see, they this alpha quantity is not that much varying compared to the like surrounding things. I don't think it will weigh that much. I mean, okay, you should take it into consideration, but after like this topic, I have never seen it actually being into play. We will see. Like in future, like in next semester, I'll be like we have a topic of design structures and all. I don't know if this will come in there. We need to see. I also am not aware of it. We will see. So yeah. So the stress developed here, you can write it as I'm taking as E temp. This is the strain developed by this is it's equal to alpha into delta t. Alpha being coefficient of expansion of the material, like it depends upon material to material, and delta t is the change in temperature. And yeah, E temper into length only, no, because yeah, length. Okay, sorry, this is not okay. This is not technically your okay. This is your strain value. Yes, correct only. This is your strain. Let me write. This is strain is equals to del L. So this is your sigma value. Sigma being your the expansion. What is this? This means what should I understand? Right? What is it? Alpha delta t into L. So this is your strain value. Strain is nothing but like percentage, like elongation divided by original length. Yeah, elongation divided by original length. So your strain into length will give you elongation. So elongation is equal to alpha delta t into L. So this basically are the strain values. Based upon this and depending upon the nature of the material, you can also calculate stress developed and all. Depends upon the you do it. I'm not doing it. Fuck you. How much charging is this? 8%. Okay, I can manage. Hmm. You know, there's actually a topic in the syllabus, not syllabus technically. What in my notes called misfits. Initially, when I wrote misfits, I didn't get like it's like okay misfits. Now I'm like, oh my god, misfits is a boxing thing. Why am I telling this to you? I don't know, but listen, it's important. Part of syllabus will come in exam and okay. What else is this? Let me see. Someone messaged me. Is that the park? I'll chat here easier. When did you keep this? 5 minutes ago, I didn't even see. No, like, no, man, you can't see. Nice. Okay, let me see the next topic, which is this. Yeah, temperature is over. I think like I can go to strain energy and all. This is the topic where it gets kind of interesting. Oh no, I still have EG relationship. Let me complete that. There's a derivation for this and all. I'm not telling you a derivation because I myself don't want to go through it again. But let me see what it is. E G V. It's not technically V, but okay. Relation. Yeah. So basically, it's a triangular story. You're trying to find how they're related and all. Let me see. So let me actually say what's EGV. E is your Young's modulus. G is your what is G? It's your the rigidity modulus. Yes. And V being your the V is nothing. V is same as mu, which is your Poisson's ratio. Okay. So there's a relationship for three of them, which is given by. I'm not going into details of the derivation. G is equals to E by 2 into 1 plus mu. Yeah. Yeah. So your distributive modulus is equals to Young's modulus divided by 2 into 1 plus the Poisson's ratio. Let me write it a little bit. Right. Yeah. So this is a derivation easy only, man. It is easy, but charging less, and I want to jump into SFD BMD, so I want to avoid it. Yeah. So again, using this relation, I can relate it back to bulk modulus. I'll explain you what is bulk modulus. Bulk modulus is basically like how should I explain bulk modulus? Like you have we have seen more use of this in fluid mechanics. Bulk modulus basically means that uh, okay, let me take example of Young's and rigidity to explain what's bulk. Young's we know. Young's is basically when there's like tensile or compression stresses like forces acting on the body. The resistance towards it is Young's modulus. Like all the behavior of the body under those conditions is given by Young's modulus. Rigidity is when the force acting along the body. So there's a percent like delta, not delta. There's a angular deformation. You can say angular deformation is studied under rigidity modulus. But our bulk modulus is basically a change in the body in terms of volume. Let's say a basic example of this is you take a cube, throw it into some sea. As it goes deeper into it, because of the like buoyant forces, like not buoyant, like hydrostatic forces, the volume of the cube tends to decrease. That's the reason, like that ocean gate thing. No, ocean gate thing. What happened? Like the pressure was not balanced enough for like inside and outside. So like I think that was the problem. I don't remember. But end of it, what happened? It got compressed because of the hydrostatic forces being more than the inside of the ocean gate thing. It got compressed. Implosion. Yeah, I think that implosion is that thing only. Like the inside pressure was not balanced with the outside pressure. So yeah. So that's what. So bulk model is related to that, like resistance to body in change of volume. You can measure it with the help of bulk modulus. So how is it given as? Let me write. So this is let me not erase it. Wait. Yeah, K is equals to K. I'm writing as bulk modulus is equals to E by 3 into 1 minus 2 mu. And K is your bulk modulus factor. So yeah, this is bulk modulus. Bulk modulus. By the way, do you like my style of denoting modulus? I'm the only one who uses it because modulus. I'm so smart. Yeah, let me continue. So these are your EG relationships. So yeah, EGV and bulk modulus. These are the relationships. Now let me get into strain energy. This again, this kind of interesting topic. I kind of like it. I think I'll do this. I'll keep charging and I'll come back after like 8 o'clock and I'll continue. I'll go gym boy. By the way, I'm close to completing this. Like I completed this like the not mock script. What do I say? Like yeah, I wrote the points which I'm going to write in the script. You know what the script is about. I'm not going to reveal it here because there are other people watching this. So yeah, so the script I completed kind of. I'm writing screenplay also for that. Like way to do. So I have been thinking about what like I'll do in my house only. So I have been thinking about what all camera placements I can use in my house. It's such interesting things. Yeah, I can. I mean, I don't know, it kind of excited me. I'll share all of this to you in call later, private. Private times. Night, I think we'll do call if you're free. Nice. Can't wait to criticize the shit out of it, Shad. It's okay. I appreciate your criticism. If not you, who is going to criticize me? Why am I talking to you as if you're my girlfriend or something? I mean, I want you to be, but still, it's personal. So glad there's no one else here. It's just us two. Yeah. Getting to strain energy. Strain energy. So let me talk about strain energy. So strain energy is basically okay. Initially, I have talked about when in like UTM, the universal testing machine, when the rod is being pulled. I talked about how the neck area gets decreased and it eventually leads to its breaking. But the neck area, it's when it decreases, you can't there's all a production of heat. Why does heat get produced? Because the body itself has something called strain energy. Like as the body is yielding, there's development of stress and there's a like release of energy. You can say this release of energy or the basically storage of this energy is strain energy, which gets released when the body is undergoing your the yielding. It's undergoing yielding. The strain energy tends to get released. There's also a whole theory about how the strain energy is actually related to like earthquakes and stuff. Like I'll tell you. Actually, I told you this already, but still I'll tell you again. Like you know how the rocks or the any rock bed within Earth, they're under constant force or constant pressure due to its surroundings. So when like it gets to a point where they can't take this stress anymore, so they tend to rupture or they tend to fail. So when they tend to fail, all of the stored energy gets released. So you can say this like this release of strain energy is what causes your earthquakes. Like it gets released in forms of seismic waves. So that's why it leads to earthquakes. Like it's kind of the similar thing. It's a theory which I read in like geology. I thought it was cool, so I thought, okay, let me share. So yeah, so strain energy. Let me see how we can indicate strain energy. So strain energy. First of all, the energy stored in the body can be indicated as. Oh, wait, there's something for it. I forgot. Yeah, half into stress into strain. Yeah, can you see this shit? You can't. Let me try it again. Okay, half into stress into strain is your you can like that's your energy stored in the body. Like stress and strain depends upon when the body is yielding. So yeah, I switched to laptop. It's clear only. Oh, good, I guess. So this if you like if you write the value of stress and strain and you simplify it, you can write it as uh, p square by 2e into volume. Yeah. So this is how you can indicate your energy stored. Based upon this only, you are the like how energy is being released or the energy is being worked against external factors. We'll study using this. Basically, this is your work energy theorem only. It's just an application of work energy theorem. I'll show you how it is related with. So, how does strain occur in a body? Strain occurs when a load is being acted on it. So, this load can be categorized into three types. So let me keep this towards side. So the first thing is how the load is acting. Hmm. The first thing is gradual loads. What are gradual loads? Gradual loads basically mean that how much explain that? Like the force, which is like the force or the load acting on the body, it increases gradually along with time. Like let's say the rate of loading is 10 kilonewtons per second. Like first second 10 kilonewtons, second 20, 30, 40. It keeps increasing gradually or you can also like kind of like linearly. So that's gradual loads. So here the how you can denote this is your the work by external loads. You can write it as half into P into delta. Usually, like work is how do we usually denote work? Work is nothing but load into your the delta component. Delta is nothing but elongation. Like that's how you usually denote work done. But you're using half here just to indicate that it's a gradual load. Like because it being a gradual load, like if you look at the graph of it, it's kind of like a triangle. This being P and this being your delta. So yeah, we take the area under this graph to be mean basically. Yes, I'm explaining graphically. Like area under the graph usually it's a triangle, so half into base into height. You can take it like that. It's not basically mean. It's just the area under the graph being half into p into delta. But yeah, you can take it as a mean component because it's a gradual load it's being acted. Like mean also, I think it comes from this one. Like you take half as mean for like other thing. I don't remember technically, but this is what I stated. This is what I'm saying. To graph. I hope that's okay. Is it okay? Yes. Okay. Let me continue. So there is a work active external load. Now let's say at work stored in body, that is equals to half in delta. Okay. This P dash is stressor and A is area, and this thing is delta. Delta is nothing but again deformation. Is P the highest value or slope? Uh, I think P indicates the rate of loading. Like I think 10 kilometers per second. I think the 10 is what indicates like it's increasing with a factor of 10, no? So I think P is that. Or I don't know actually. Wait, good question. Let me see. Textbook is here only. I feel like P is a load. Yeah, I think slope only. Let me see. Waste energy. Energy. 178 page number. Hmm. Wait, just soften this book only. Highest probably. What? Yeah, that's what I'm also thinking, but I don't know. Like, where is this thing? I can't even find it. One second. Yeah, I think it's a slope only because it says let the axial load P be gradually applied gradually to a bar. So it's like increasing by a term of P each time. So I think it's like the rate of loading P. Yeah. Okay. Can I continue? Nice. Okay. Yeah. So this is your the work by external load, and there's a work stored in the body. Here P dash is the stress which is developed within the body. That's why we are concerned about. We are finding that only. So if you equate them both, what will you get? You will get that P dash is equals to P by A. So yeah, I mean it basically results in just your the force which is being acted divided by area because it's a gradual load. So this is your first case. And let's go to second case. Uh, I was about to say, are you noting this down? But I realized no one is noting this fucking thing down. Okay, let me continue. Now instead of gradual loads, we'll go to sudden. Sudden basically means that gradual means from let's say from 0 to its peak value, it's increasing gradually, like under the time of delta t. Whereas sudden it usually goes from 0 to 100 real it let's say how should I explain this? Let's say okay, this is my handle. Let's say there's a beam, and I'm trying to apply a load on it. I'm trying to like hang a load on it. Let's say I have let's say there's a hooker, and this hook has a 10 kg load on given to it. So if I just like hook it suddenly, like hook onto it, it initially has zero load, and as soon as I hook it, it goes to 10 kg load. So it's a sudden implication of load is sudden load. It's in the name only, but I don't know why I explained, but still. Sudden loads. So work by external here the work by external load is just given by P delta. we are removing the half term because it's going to 0 to 100 real quick. That's a meme reference if you understood it. I appreciate it. But yeah. So again, but work stored in the body. Someone message. I think you want. Yeah, it's supposed to be a meme reference. Like I no, I thought only you would get it, and you got it. So good job, I guess. He actually said also. Okay, let me continue. So yeah, work student body is equals to half. Again, the work student body is not. There's like no change in it because it's the body which like it's the body trying to resist the loader. So half into PA into A delta A. So again, we consider PA. If you do it, you just get half of it. So P dash is equals to P by 2A. So it's just sudden the stress developed with sudden loading, just half of what you get in a gradual. Wait, is it half? It's half only, no? Yeah, it's half only. Wait a minute. Hmm. P by wait. Oh, never mind. Half is here, so it'll go that side. Never mind. So P2 will be in the numerator. So 2 by P. So it's twice. Sorry, it's not half. It's twice of what you have in gradual loads. And now we'll go to impact loading. Impact basically means that see, I told you like I was going to hook the load onto the bar instead of like hooking. Let's say from a distance of x, I'm leaving it because I left it. The load 10 kg load, it'll act on the body, but it'll strike the body with some velocity. So that's what basically impact means. Like that's a way of defining impact. Yeah. So we'll look at impact loading. Wait. Impact loads. So impact loads, I'll erase all of this shit. Because impact loads, you like the stress in impact loads, you can find by energy conservation. I'll show you it. That's what I was saying. Like this was the energy conservation what we did right now, but now we'll write it. Let's write it. So P. Okay, let me first draw a diagram for this. Wait, I'll do the same diagram. Yeah. So let's say this is a like bar. The bar has a little like kind of like a cliff, not cliff. What do you call this? What like wedge and web and flange? No, I think yeah, this is web and this is flange. I guess I don't know. So it's kind of a T section, inverted T section. So what happens? Let's say there's a load P here. P is released and it travels through a distance of HM. So it comes and strikes this web of that inverted T section. So P. So what is the opposite? So is this flange? The horizontal thing is flange and the vertical thing is web. That means what should I understand? Puka was charging by the way. Bro, 1% charging. Fuck it, I'm ending it here. We will discuss this later. 6 o'clock I'll go. After I come, I'll come. I'll keep the link again. We'll discuss then. Because I am scared that if I don't shut this right now, I'll lose the video or recording. That's why I'm ending right now. So bye 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 bye.